A couple of videos ago, we said that functions were a way to declare some code that we could have then later reuse in our own code. And since in order for us to have a function, we need to provide some code, what happens if we call our function inside the code that we assign to that same function? Well, congratulations then, since you have just discovered recursion. And if we look around, there are many things that are themselves recursive in nature. And actually, I can show you one right now. This is the program that I'm using in order to record a video. And right now, since the program is recording the screen and then showing me the screen itself in the program, if I put the program inside the screen that he is recording, then we get a recursive image of the screen showing a screen, showing a screen, showing a screen, and so on. And this is one of the many way to see how recursion works also in the real world. Getting back to our code, recursion is a very powerful tool that we can use while coding, and we can use recursion in function, but also later in the course, we will see that there are also data structures that are intrinsically recursive. We can use recursion in order for us to define a factorial, and in math, we define a factorial operation by the exclamation mark after the number. There are also extension of the factorial operation, but we will not focus on those extensions. And so we say that the factorial is only defined for positive integers, and it is so defined. The factorial of 0 is 1, the factorial of 1 is 1, and the factorial of any other number is that number multiplied by the factorial of the previous. And we can see where we are going. In fact, the factorial of a number is defined by the number itself multiplied by the factorial of the previous number, which means we have to repeat this step as long as we do not encounter 0 or 1. So we can start declaring our factorial function, and we say that if the number provided as an argument to the factorial function is equal to 0, and we are in this case, then we want the factorial of n. So we want the factorial of 0 to return 1. And we want the same for the factorial of 1. Of course, this line of code is a bit repetitive. In fact, we can just take this condition and put with an for here. So what are we saying here is that if n is equal to 0 or is equal to 1, then in both cases we want a 1. Otherwise, we want to return the n provided as an argument multiplied by whatever is the result of the factorial of the previous number. And that's it. That is all we need for the factorial. We can actually test this by doing some function call inside the for loop so that we can test actually 10 values from 0 to 9. And by running the program, actually it would be useful also to print the original number so that we know what is the result of what. And we see that we get 1 and 1 in case of the 0, then we get 2 for the input of 2, and that makes sense since we are doing 2 multiplied by 2 minus 1 factorial, and this is 1, So we are actually doing 2 multiplied by 1, which is 2. Then we have 6 as result for 3 factorial, and that makes sense since we are doing 3 multiplied by 2. Then from 4 we have 24, which is of course 4 multiplied by 6, and so on. Now, when dealing with recursion, it's important to keep in mind that there can very well be some cases in which the function never ends, and it is actually similar to an infinite loop that we saw while talking about while loops and for loops. We can see this actually already with our factorial function. In fact, if we provide a negative number, then what is happening here is that now n is different than 0 and different than 1, so it never returns 1, and it will try to return -1 multiplied by by the factorial of the previous. And what happens here is that this case is always false, and so we will get always here, and we will always try to compute a factorial that will never end. So if we now run the program, we see that we get an error, and the error is curious since it says maximum call stack size exceeded. What happened here is that each time we call a function, then a little portion of computer space is dedicated to that function. If we keep calling function, at a certain point we run out of memory, and that is exactly what happened before. And so in order to prevent this, we could add a condition in this case that says if n is less than 0, then return 0, and we know that there is no value that returns 0, so we know that this is some kind of error. We will see also some more appropriate way to say that the input is something that we did not expect, but in this case we just want to return 0. So if we now try to print the result of a negative number, we get a 0, so we know that we are in this case. And also, if we try to do something with non-integer values, since this will be false, and we will always try to get this evaluated at some point, keeping removing 1 from the number, we will get to some number that will be eventually less than 0, and in that case we'll also have 0 as result. And just to be clear, we could have defined the factorial also with some kind of loop, and in this case I used a for loop, and I do that by keeping the first condition just to be sure to be operating with positive numbers, and then declaring a variable that holds a 1 by default, and then by entering a loop that starts from 1 and goes on until I reaches the number n that we provided, multiplies whatever it is inside the result by the I. And if we do some steps, at the first steps we'll do 1 by 1, then we'll do 1 by 2, then we'll do 2 by 3, then 3 by 4, and so on. So this is actually the factorial, and once it reaches the n, and when I actually is greater than n, it exits the loop and just returns whatever is inside the result after all this multiplication. And if we run the program, we see that we get the same result for the factorial loop or also for the factorial, and we see that those two are equal. So we started this video by explaining what recursion is, and we saw that we can actually call a function also in her own body, we also saw that it's very well possible to never end a recursive function, and that is not actually a good thing. And in fact, recursive functions are very similar to loops. In fact, we can almost always rewrite a recursive function under the form of a loop, but as in this case, writing a recursive function took way less line of code than writing the loop equivalent function. And later in the course, we'll also see how recursion is a very powerful tool. So if you learned something from this video, consider subscribing so that you can keep learning with me, and also like the video. In any case, thank you for your time. We'll see you in another video. Bye bye.